So yeah, I have to say, David Beasley made me both feel proud that I kind of understand what's happening in PyPy and bad because it's not actually that hard. This is both an advanced, listed as advanced and on the expert track. So if you don't know what PyPy is, this may not be the best talk for you. However, David's keynote, which I wasn't expecting, probably prepared most of PyCon for this. I'd like to start with a joke which I stole from a presentation I saw by Kenneth Wright. And he quotes our favorite line from the Zen of Python: if the implementation is hard to explain, it's a bad idea, except PyPy. Okay, so I'll start with the overall design principles of the PyPy JIT. One of the most important ones is that it's interpreter agnostic. We do not actually have a Python JIT. We have a JIT generator, which generates JITs for interpreters written in our Python for the PyPy translation toolchain. So this works pretty well, but the JIT generator is not perfect and it cannot generate a fast JIT immediately, or the fastest JIT. So we have to allow the language implementation, the interpreter, to be able to help the JIT with type inference, for example. And our JIT in PyPy is a tracing JIT, which means that we take to heart the idea that 90% of your time is spent in 10% of your code. And we compile only the code which it seems like is being run repeatedly through the interpreter, which means hot functions or loops. And optimizing dynamic languages for assembly generation is a bit different than static languages like C. I'll talk about optimizations later, but essentially what we do is we have to remove all the indirection, which is in dynamic languages. Because in Python, you get lots of power from being able to dynamically assign attributes to instances, for example, but it also adds a lot of interpretation overhead. And the last thing we try to do is make our JIT fastest on code which is simple and idiomatic in Python. And so, while you can put a million different types in a list, that code is not necessarily going to be the fastest on PyPy JIT. Also things like introspection, like introspecting the stack frames and debugging information is not the fastest on the PyPy JIT. So the several components of the PyPy JIT, which I'm going to be talking about, is translation, where we actually generate the JIT from the description of the interpreter. And then I'm going to talk about how the JIT works at runtime, specifically tracing, how we optimize the result of tracing, and assembly generation. So to add a JIT to your interpreter in RPython is actually very simple. You just need to modify your interpreter source to add two special functions which the RPython translator will later recognize. And I'll show you later how this works in the Python interpreter. The two hints are called canInterJIT and JIT merge point. JIT merge point tells the JIT when it's safe to return to the interpreter. And usually that's at the head of the bytecode dispatch loop. And canInterJIT surprisingly tells the JIT when it should enter. And this is at the beginning of loops, once a loop has been closed when we can enter. And the JIT also needs some arguments, which is basically the data which the interpreter is working with. And these are classified into two categories: green variables and red variables. And green variables are constants. They never change during the loop. And so here, let me show you what's in the Python interpreter. So on the Python interpreter, the constant arguments are the code object and the instruction pointer, because when we enter the JIT, those are always going to be constant for a given loop. And then the reds are the frame object and the execution context. In the Python interpreter, the frame object is an object which stores the local variables and the value stack for a Python frame. And the execution context stores thread local data basically, like exception state. So this is a simplified view of how we have inserted the JIT hooks into the Python interpreter. That while true loop is the bytecode dispatch loop. So we have a JIT merge point every time we go to dispatch a bytecode. And the jump absolute bytecode is a Python bytecode which tells the interpreter to jump to some other bytecode, and it's at the end of loops. So that's how we know that we've ended a loop. So to get a JIT, we have these hints in the source, and then we go to translate our interpreter. And as Dave Bealey said, what happens is we have the interpreter halfway through translation in a bunch of low-level flow graphs. They're in a modified singles assignment form, compiler intermediate representation, and they have low-level type annotations on them. Like it says, add these two integers, or add these two floats, or access some value of a structure. And so what we have this flow graph description of the interpreter, and what we do is the JIT generator takes these and it basically serializes them into a representation which we can write into the binary. So what happens at runtime is we'll have a description of the binary in terms of the serialized representations of the flow graphs, which we call JIT codes. And we'll see how those are used. And so now I'd like to introduce the example I'll be using to show how the PyPy JIT works. It's a very dumb primality test, trial division. But it works well with PyPy JIT because we're really good at optimizing integers. So this is what the bytecode looks like. I just wanted to point out that there's a lot of manipulation of the stack. Like this load fast opcode, these load fast opcodes, they load these variables and they push it onto the stack, and then this operation will pop them off the stack and compare them. And so we're going to see later how PyPy JIT optimizes out all this miscellaneous stack manipulation. So now we have a PyPy binary, and we're running it on some Python code, say my primality test. And the runtime part of the JIT keeps a track of every loop and every function call which happens in the interpreter.